Yeah, g'day. I'm starting to build a motorcycle engine, a 1920 Redrup 3-cylinder radial engine. So if you like a mix of casting, machining, motorbikes and history, please subscribe, come along for the ride. Now viewers to my channel know that I've got quite a well-equipped machine shop here, but also that I mainly make tools for improving tools to make other tools. And this leads to the inevitable question, like from my sister.
So why do you need all this stuff? What have you produced?
Yeah, ouch, that hurts. So it's about time I actually did something productive with my machine shop. Now, every Kiwi with a lathe sooner or later thinks they're Burt Munro or John Britton. I mean, all Kiwi YouTubers sooner or later make their own motorcycle engine. I'll leave a link up here to odds and ends machining. Now, a few years ago, one of my kind viewers, Henry, gave me a book. This book. It's the biography of Charles Redrup, an early British piston engine designer. Now he did quite a bit of aviation, including designing and building an engine for a biplane in World War I. And as we go through this series, which will probably take at least a year, probably longer to make this engine, I'll fill you in on some of the details of Charles Redrup's life. But it's this little 309 cubic centimeter 3-cylinder radial motorbike engine which caught my eye. I love the aesthetics of this engine. Being a cross-flow side valve head design, a so-called T-head, gives it a very appealing looking lozenge sort of shape, but also left my head scratching of how the actual valve timing works. So through his publisher, I contacted the book's author, Professor William Fairney, who's been very supportive and I really appreciate his feedback. Bill provided me with a GIF which shows the epicyclic valve actuation. I'll show that in a later video once we actually get to it. He also answered many other questions which I had on the engine. I'm going to leave a link to his book down in the description below, and I really recommend you buy a copy, both to reward Bill for the time and effort he put into researching and writing it, and also because it's a very good read and it'll help you follow on what I'm doing here in this series. Now another aspect of the design which attracted me is that it's a radial engine. Now, you know, I work in aviation, so I've always had an affinity for radials and other aero engines. Now, Charles Redrup designed a number of different radial engines, and later in his career, he also moved on to more axial piston engines. Now, of course, any project which I undertake has to fit within the capacity of the machines which I've got. And one of the nice things about this engine is that its maximum diameter of a single part is only about 270 millimeters or 11 inches, which is right on the boundary of what my lathe can swing. However, I'll probably end up machining the core parts of the crankcase using a boring head on the milling machine. Now in discussion with Bill, he used to own one of the surviving engines, and the crankcase with its integral cylinders is actually cast iron, so it's going to be a real challenge for my little backyard foundry to actually do that casting. Now once I started taking a close look at the limited number of sketches and drawings and photos which are in the book, I started to see that there isn't really just one single frozen design of this engine. As you switch between photos and drawings and actually start counting the cooling fins, you can see that really doesn't seem like any two of these drawings or photos or anything is actually of the identical engine. So Charles Redrup obviously sort of iterated on his design over the period which he manufactured it. It was never made in any great numbers. This model of engine was first produced in 1920 for motorcycles, but also for generators and other stationary uses, but it's not clear how many were actually built. Now, since there are so many differences in the different engines shown in the book, I'm going to have to basically pick one. There is in the book a nice sectioned two-angle drawing of one of the engines, so it kind of makes most sense that that's going to be the one that I'm going to base my replica on. Now in my correspondence with Bill Fairney, the author, we did have a bit of a discussion about fasteners. Now in 1920, it would have been quite common for British motorcycle engines to have British standard cycle threads. However, Charles Redrup had come out of the aviation industry of World War One, and therefore that was probably going to be more British standard fine threads. Bill asked around and came back to me that yes, it does look like British Standard Fine was the thread system which Charles Redrup decided on for his motorcycle engines. So that's what I'm going to use. I'm expecting I'm going to have to make basically all fasteners on this thing. Now, I've had this project on my to-do list for over 2 years. After first reading the book, I decided this is the engine that I really want to make. However, the hardest part about starting is starting. So late in 2024, I set 2 New Year's resolutions. 1, don't make so many mistakes and crashes that I need to make another a year in crashes video. And 2, get started on this motorbike engine in the new year, straight away. Now in December I was still procrastinating, but between Christmas and New Year's I finally knuckled down, and the first thing I had to do was just import that drawing into FreeCAD, scale it, and move it to put it on a center. Luckily, one of the photos that Bill sent me was actually a higher resolution scan of that drawing than I got photocopying it out of the book, so that was very helpful. Thanks a lot, Bill. To be able to draw off an existing drawing or illustration, I'm going to need some dimension. Luckily, it's written right there on the top of this drawing that this engine has got a bore of 2 inches and a stroke of 50.8 millimeters. What they call a square engine, and that then meant I could scale the drawing off the bore. In my career, I've done a fair bit of maintenance and also airline management of aero engines, but of course that's mostly turbine work. Now, I've never built an engine myself, and I've also never reverse engineered anything this complex in CAD before. I could see a danger of analysis paralysis if I first tried to model the entire engine in CAD before I started making anything. So to avoid that analysis paralysis, what I decided to do was to pick a single component that had limited interfaces to other components and also had no critical function in the stack up of tolerances. So that first component which I've chosen is the piston. Now the advantage of the piston is that the information in the drawing seems reasonably complete, and it only interfaces with the gudgeon pin, the cylinder, and its piston rings. Now as soon as I started modeling, questions started to pop up quite quickly. This is a piston from a much larger aviation radial. How is the gudgeon pin restrained in its pin bores? Most modern engines either have circlips on either side or some sort of like mushroom shaped pads to hold the gudgeon pin centered. But it looks like Charles Redrup designed it with the lower of the 3 piston rings centering the gudgeon in its pin bore, which seems unusual. Now, one of the consequences of having that 3rd ring retain the gudgeon is that the pin is much higher up on the piston than is typical on modern designs. Okay, so all of this led to more research, otherwise known as procrastinating and watching YouTube videos. The best YouTube video on how to design and cast pistons is by the old foundryman, Martin. I'll leave a link up here in the corner. And in his videos, Martin refers to a book by Steve Chastains. I went looking and I couldn't find that book. That book's not available, doesn't seem to be in print anymore, or at least not here in Europe. But Googling it, it popped up as a PDF on some forum, so that was helpful. It's only like 34 pages. I read right through it twice. Very, very helpful. Now I can see that one constant challenge is going to be the desire to change or improve or simplify things as I go along. And there's a saying in the home-built aircraft community, change one thing, change everything. So I would like to do a real replica and stay as close as possible to Charles Redrup's design. Because once you start improving a design, it just creates a whole rat's tail of redesign work. So first up, I modeled the piston. While the exterior is pretty simple, of course the interior's got a little bit more complexity to it with quite a few fillets and intersections. The next part I modelled was the piston pattern. Once again, this is a pretty simple component, and it's got 2 integrated risers on the side to feed the thicker parts of the pattern. I then sent that model to my Bamboo Labs X1C printer. I'm just printing this in PLA. There's no special need for any specific strength or anything with these pattern parts. While I was doing that, I figured I might as well also print out a runner that can go in the mould as well. Right, so first up, there's the piston pattern. More challenging than the piston pattern is the core mould. To make that nice curvy internal surface of the piston, you first have to basically cast a block of sand in that shape, and that's what you need a core mould for. Modern 3D printers are an absolute godsend for this sort of application. The surface finish is so good that you can basically just use it straight off the printer. The striations are so minimal that the sand doesn't really hook into it or bind to it. There's my core box. I just need to put in the alignment pins. When I cast the piston, I also want to cast a void as a pilot for the piston pin hole. So for that, I've also made up another core box just to make a little stick of sand. I've made round core molds like this before. The advantage of doing them like this is they're pretty flexible, so it's quite easy to spread it to get the core out once it's made. The bottom cap here holds one end of it together. A ring at the top holds the other while I'm ramming it up, and there's a hole in the back. For this gudgeon pin core to work, I'm going to need a hole down the middle of it. So this is just a piece of TIG welding wire. So that can go into there, like that, and I'll probably just cut a second bit of TIG welding wire to use as a rammer. Right, I'm going to have my first shot at this sodium silicate bound sand core. So this is just cheap place sand from the local hardware store. I'm going to try making up 2 cores at the start just to see how it works. So let's call it 150 grams of sand per core. Now in Martin's recipe he adds 0.5% of glucose powder just to make the core break up a little bit easier. So I need 1.5 grams of glucose, but I don't have glucose, so I'm trying sucrose. It's just icing sugar. Right, that looks close enough. Just give this a little stir in before I start. I remember when I was a kid, when my mum did the baking, she always used to put the icing sugar through the sieve to break up the little lumps. As a first attempt at mold release, I'm just using my wax corrosion spray. I have no idea whether this is going to work. I may have to go searching for something that's more effective, but hey, wax generally works as a pretty good mold release. So I whip this pin up on the lathe, it just forms the void which this then goes in. Next up, the sodium silicate. Martin's recipe calls for 7.5%. So for 300 grams of sand, I'm going to need 21, 22, something like that roughly. He did say that was a pretty strong mix, so oh, there you go, 22. To mold this sodium silicate into the sand, I also do it the same way that Martin suggested, where first you mix it a bit and then you just push it through a sieve a couple of times. Right, now let's ram this mould. I was told to be generous with the venting holes in it. Put vent holes in from the sides so that I can get in there with the CO2 as well, and also in from the bottom. I do have my doubts as to how well a core this small is actually going to work, but hey. Right, now to harden this thing. Printed up a little adapter here. gas down that hole. Right, that's all well and good. Now let's see if I actually get the thing apart. Whoop. Okay, well, I now know I need a better mold release agent. How about the tiny core? Righty, now you can see why I made this so flexible. So it just kind of drops out. Just rub off the excess sand. Because the next question is, can I actually thread this thing through the core? So I need a significantly bigger hole for it to go through cleanly, I think. That was a good first attempt. I know what I need to do next. I guess I'll increase the size of these holes, make a larger diameter pin to give me more clearance to this thing. Since the wax didn't really work, just clean this out as well as I can. And for my next attempt, I'll try using talcum powder as my parting. Nope. Okay, that's releasing way worse than the first attempt with wax. Well, one of them came. Now supposedly you can use super glue on these cores, but I have my doubts. I think it's just going to disappear straight into the... No, that's good. Well, this wouldn't be my first choice of how to build it, but if all else fails... Bugger. Let's try a bit of sandpaper on this just to reduce the diameter a little. Hey, did you guys see that Charlie Dallin finished the Vendée Globe round the world solo yacht race in 69 days, absolutely smashing the previous record? Now for what that really means, I'll leave a link up here on the right because Conrad Coleman expressed it better than I ever could. For attempt number 3, first thing I'm going to do is open up these holes a bit. Going up 0.5 millimeter, I'll use the actual drill as the arbor. Alright, don't really want to cut my fingers on these sharp flutes of this new drill, so I'll just put a bit of tape on there. Right, next thing, I need to try out a different wax. This is just some furniture wax, so let's see how this works as mold release agent. Of course, the bit that needs it most is the bit that's going to be hardest to get to. I also printed a second mold where I tried to increase the radius down in those bits by as much as I could. Unfortunately, the CAD doesn't really give you much option. It's kind of limited by the ability to calculate the intersecting fillets. I really think I'm going to have to revisit this whole design and just reduce the depth there and somehow come up with bigger radiuses, because this is not working. However, did enlarging this mean this is going to fit better? All right. Now to give myself bigger radiuses down through here, I think what I'll first try and do is degrease off that wax. I'm not sure if that's a thing, but maybe brake cleaner will take it off. And then I'll just use some epoxy and try and make bigger fillets. Now I have no idea if this is going to work. It might just turn out to be a big mess, but let's give it a go. Okay, this epoxy actually seems to slump down quite nicely. I guess I'll need to put it up at an angle on a heater and let it slump down and fill up that corner a bit and then dry. Right, well, those epoxy fillets have dried overnight. Let's hope they're going to work. I'll give them a layer of wax to help with mold release. Partially worked. Well, only losing one ear is a bit of an improvement. That was some sand which I mixed up yesterday, and it was a little bit crusty already. Right, now failure number 5 was getting closer, but I noticed when I was packing the sand that it was feeling kind of crusty, because it was sand which I mixed with the sodium silicate yesterday. So what I'm going to do is make up a fresh batch and have another go at that one. Still didn't come cleanly. Again, 3 out of 4 broke off. Okay, taking a closer look at this, I think this epoxy has slumped a bit and given me a little bit of an undercut. So let me grind a bit of that away to make sure I've got a positive fillet. Maybe on the other side as well. Maybe a bit of dressing in there could help. Okay, I think in this one I'm going to need to put just a little bit more epoxy. Still got too much undercut. Right, I've now gone through and just add a little more epoxy to make those fillets more rounded. That's now been sitting on the heater for a couple of hours. I won't start grinding it yet because it's still maybe a little bit soft. I think I've got rid of all of the undercuts. So what I think I'll do now is mold it and see what happens. Like, I've still got a few little bits of a few ripples and stuff in it, but I can grind them back later when it's fully cured. All right. Well, nearly got it. Constantly improving. I'm up to only 1 out of 4 failed. Well, it looks like I had a bit of a soft spot there that maybe didn't gas properly. Right, well, at a pinch, number 7 is probably a usable core. Hopefully I can get them come out even better than that. Okay, so I think I'm making progress on this. I'll need to do a wee bit of playing around with the die grinder and the epoxy and try and get that final part to release. Yeah, there's just definitely a bit of cleaning up and smoothing work that I can still do on that epoxy, so maybe that's enough to get it to release properly. Maybe it was okay and I just didn't gas it enough. I'll have to play around with that as well. Overall, I'm pretty happy with how this is progressing. So as soon as I can get it to reliably release its core, I can go into mass production of cores, and then in a future video we'll be doing piston production. And once again, a big thank you to Bill Fairney and also to Martin, the old foundryman, for their assistance in this. I really appreciate it. I think my next video is not going to be on this project because I'm in the middle of a heat treatment oven build, which should hopefully be finished for my next video. Now, if you're a Patreon or a channel member, you've probably noted here that I've put up the next live stream date here. Unfortunately, since I put that up, a work trip's come up, so I need to amend that. I'll send out a reminder about it, but instead of being Tuesday, it's now going to be on Thursday. Come and join me. See you later.